Welcome to this session where we are going to be discussing linear programming with a limiting factor. This is a continuation to the previous lecture we had under limiting factor, where we discussed allocating resources for a product where there is only one limiting factor, where we looked at the allocation of the limiting factor based on the contribution per limiting factor. So we take it up one step further to discuss where there is more than one constraint or there is more than one limiting factor using the graphical linear programming method. So when there is more than one limiting factor, the contribution per limiting factor method that we looked at earlier cannot be used. Instead, we use linear programming using the graphical analysis and simultaneous equations. This linear programming is different from the linear programming under computers. So do not mistake the linear programming under computers with this one. It has got nothing to do with computers. So the linear programming method under limiting factor takes us through a number of steps. The first step is to formulate the model. In formulating the model, we have our first step, which is to define the variables. After defining the variables, then we establish the constraints, generally in the form of amounts of resources used versus the amount of resources available. After we've established the constraints, then we formulate the objective function, which is solving the problems using the graph only if there are two variables. After we have formulated the objective function, then we try to solve the problem using the graph. So we plot the constraint on the graph. After we've plotted the constraints on the graph, we then identify the feasible region. The feasible region, which is the region where these combinations of variables which are possible within the constraints, within the resource constraints. Once we have plotted the feasible region, then we plot the slope of the objective function, which is also called the ISO contribution or profit line. We then use this ISO line by sliding it to find the optimal point. So if you are trying to maximize the objective function, you slide the ISO line away from the origin. And if we are trying to maximize objective function, then we slide the ISO line towards the origin. Then finally, we calculate the value of the objective function at the optimal point. So we are now going to look at an example where these steps are going to be demonstrated. So we have this example question. WCOR manufactures two products, A and B. Both these two products pass through two different departments, the mixing and the shaping. The organization's objective is to maximize contribution to fixed costs. We are told product A is sold for $150, whereas product B is priced as $2. There is unlimited demand for product A, but the demand for B is limited to 13,000 units per annum. So meaning if we produced more than 13,000, we will not be able to sell the excess above 13,000. We are then told the machine hours available in each department are restricted to 2,400 per annum. Then we are given other relevant data as follows. We are given the machine hours required in each department for each product. Product A requires 0.06 hours in the mixing and 0.04 hours in the shaping, whereas product B requires 0.08 hours in the mixing and 0.12 hours in the shaping. We are further given the variable cost per unit for each product. Product A 130, product B 170. What are the constraints in the situation facing WCOR? So we go through the steps that we have just been looking at. We said step one was to define the variables. And the variables are the items whose value we are trying to decide. In our problem, the variables are the two products that WCOR can make and sell. In this case, product A and product B. So for the graphical method of linear programming to be possible, there can only be two variables. The variables in this problem will therefore be stated as follows. So you can use any symbol to state your variables. In our case, we use X and Y. So we'll say let X be the number of units of product A produced and sold, while Y be the number of units of product B to be produced and sold. Once we have defined the variables, then we establish the constraint. Please take note that even though it may seem to be a long process, under exam condition, this is a straightforward process. You don't need to do all the explanation that we're explaining. You simply quickly define your variables and then you move to establishing the constraints. The constraints are anything that sets a limit or a minimum limit on the solution. So typically, there may be a maximum limit to the sales demand for each product, or a maximum limit to the amount of production resource available, such as the quantity of materials, the labor time, or the machine hours. In our problem, there are constraints for the maximum sales demand for product B, which we are told somewhere as being 18,000. And then there was a restriction on the machine hours available in each department to 2,400. Each constraint must now be stated as a formula or inequality. An inequality is similar to an equation, except that the symbol less than or equal to is replaced by an equal sign. So let's consider first the machine hours in the mixing department. The machine hours in the mixing department were given here. The machine hours in the mixing department are: product A requires 0.06, product B requires 0.07. So each unit of product A requires 0.06 hours, and of machine time producing 5 units therefore requires 5 times 0.06 hours of machine time. And more generally, producing X, which we defined as our variable, so producing X units will require 0.06 x hours. Likewise, producing Y units of product B will require 0.0 Y hours. So the total number of machine hours needed in the mixing department to make X units of product A and Y units of product B would therefore be 0.06x plus 0.08y. We can now complete our equation, and we know from the information that the machine hours cannot be greater than 2,400 hours, because that's all that is available. So we arrive at our inequality of 0.06x plus 0.08y is greater or equal to 2,400 hours. The final inequality in our case is easier. This was the number of units of product B produced and sold, which we are told should be less or equal to 13,000, because that was the demand per annum. So an inequality is therefore Y is equal to or less than 13,000 units. Then we also have the non-negativity constraints. These you will never be given in the question, but if you do not bring them out under the constraints, it will cost you marks. You cannot produce less than zero of a product. You cannot produce less than zero of a product. So since negative numbers of products cannot be produced, linear programming in this case will require that you show that your variables should be greater or equal to 0. In our case, our x and our y should be greater or equal to 0. Linear programming is a simple mathematical tool, and so there is nothing in this method which guarantees that our answer will make sense. However, an unprofitable product may produce an answer which is negative. This is mathematically correct, but nonsense in operational terms. So please remember to always include your non-negativity constraints. Again, a word of caution, the question never brings these ones out, but you are required to have these ones in your solution. Step 3, we then now construct our objective function, which would be either to maximize or to minimize. If you are looking at contribution, you'll be maximizing. If you are looking at costs, you'll be minimizing. So the objective function is a formula that states what we are trying to achieve as a solution to the problem. The objective function is always an objective of wanting to maximize something or minimize something. Typically, the objective function will be to maximize total contribution or to minimize total cost. In our problem, our objective function is to maximize total contribution. You should know the formula for total contribution: sales minus variable cost. So our sales, we are told for product A was 150, variable cost 130, giving us a contribution per unit of 0.20. For B, a contribution of 0.30. So the objective function of the company is to maximize contribution, and so the objective function to be maximized will be as follows: 0.2x plus 0.3y. So we've now reduced our problem to the following 4 inequalities and 1 equation. So we've got our equation there in the 4 inequalities. Once we are done, we now need to plot these on the graph. So drawing the constraints for our problem, we need to plot these on the graph. So we'll start with the mixing hours in mixing hour department. We have our inequality as 0.06 plus 0.08y is less or equal to 24 to 2,400. We change this into an equation by substituting the less or equal symbol with equals. Then we say if we produced 0x, so we assume you don't produce any x, how many y would you, how many hours would 2,400 produce of x? Remember, the 2,400 hours is available hours. You are trying to produce x, no, you're trying to produce y, and y requires 0.08 hours. So if x is replaced with 0, so this part becomes 0. So you now have 0.0xy, 0.0y is equal to 2,400. You make y your subject to the formula by moving 0.0x across the equal sign, so you'll be dividing 2400 divided by 0.0x will give us 0.0 will give us 30,000 y. Then you do the same thing, you make y 0, so that gives you 0 there. 0.08 times 0 will give you 0. So that leaves you with 0.06. X equals 2400. So you move the 0.06 across the equal sign to give you y, to give you x equals 4000. Then you plot these 2 points on the graph and join them up to show the boundary line of the constraints. Then we move to the shaping department. You do the same thing. You make x0, calculate y. Then make y0, calculate x. So those are the values that we get. You again plot these on the graph. Then you go to the demand constraint, where we know y is equal to or less than 13,000. So y, you draw the y is equal to 13,000. So that is the outlook of our graph. That is the outlook of our graph after drawing those constraints on the graph. Once we've drawn the constraints on the graph, we then try to establish the feasible region. The feasible region is simply the points which are bordered by the constraints. So you start from 0 here, the next boundary is there, the next boundary is there, there, and there, and back. So you simply label the boundaries of these constraints with some letters of your choice. So that's our feasible region. So you can label these. The examiner may ask you for the feasible region, so you simply label using maybe letter O, 0. Since you've got a 0 here, you may put an A here, a B there, a C there, a D there. Once we have found the feasible region, we then want to find the optimal allocation of the resources. So having found the feasible region, which includes all the possible solutions to the problem, we need to find which of these possible solutions is best or optimal, in the sense that it yields the best results for the objective function. So you can have any combination in here to produce our x and y. Any combination can be made here because this is within the constraint. You cannot make a combination outside here, outside there, this side or this side, because you don't have enough resources. You are restricted because of the constraints. If you produced above 13,000 here, no one will buy because the demand is only 13,000. So you find the optimal point within the feasible region. So let's suppose that we want to make a contribution of 3,000. Our objective function is that, which you remember from our formula. Which you remember from our formula here. So if we produced 0x, then how many y do we need to make 3,000? So you make y the subject of the formula. You find that you need 10,000 y. Similarly, if you produce 0y, you find that you need 15,000 of A to give us a contribution of 3,000. You could also have another mix. That mix combination of producing A or B, A and B will also give us 3,000. So when we can now draw our points of our objective function. That point, that line there is what we call the iso line. So we can draw as many iso lines as possible within the feasible region. So we take one of these iso lines and place a ruler on the iso line. Push that ruler outwards. We find a point at which the ruler leaves the feasible region. The last point of leaving the feasible region, that's a point at which our objective function will be maximized. That will be the point at which our objective function will be maximized. So that line there, as you push it, as you keep on pushing it, you reach a point where the last point, the iso line, leaves the feasible region. That will be the point at which you maximize the objective function. So likewise, to any total contribution of 6,000 and to any total contribution of 1,500, lines of 0.2x plus 0.3y is equal to 6,000, and 0.2x plus 0.3y is equal to 1,500 could be drawn, showing the combination of the two products which could achieve 6,000 of 1,500. So the contribution lines are all parallel to each other. They are called iso lines. Iso meaning equal. A similar line drawn for any other total contribution will also be parallel to the lines shown here. Bigger contribution is shown by further lines from the origin. Smaller contribution by lines closer to the origin. As Wx tries to increase possible contribution, we need to slide any contribution line outwards from the origin, while always keeping it parallel to the other contribution lines. we now conclude our linear programming. So as we do so, there will come a point at which, if we are to move the contribution line out any further, it would cease to lie on the feasible region. Greater contribution cannot be achieved because of the constraints. So in our example concerning WX, this will happen as you should test for yourself, where the contribution line just passes through the intersection of 0.06 x and 0 plus 0.08y is equal to 2400, and 0.04x plus 0.12 is equal to 2500. The coordinates you find there will be x is equal to 24,000 and y is equal to 12,000. So these points will therefore give us the optimal allocation of resources to produce. These are the points which will give us the maximum profit. Which will give us the maximum profit. We're saying our y is 24, our y is 12, and our x is 24. So y is somewhere there. Okay. And our x somewhere there. So that's that point somewhere there. So that concludes our session on linear programming. This is a highly examined section C topic, or in the performance management paper. You want to ensure that as you go in the exam, you are very comfortable with this topic. So I'd urge you to listen to the lecture over and over, then pick some questions and practice. The exam has now been simplified in the sense that the examiner does not require you to draw the graph, because the exam is now computer-based. The time the exam was paper-based, the examiner would provide graph paper and require you to produce the graph. They will require you to draw the isoline, to draw the feasible region, but now the graph will be given to you, and all you need to do is to identify the regions and label and be able to explain. So the explaining part becomes critical. Explaining how the isoline is used to maximize the objective function or to minimize the objective function becomes critical. So you really need to be able to explain the topic. So thank you very much for your time, and wishing you good luck as you prepare for your exam.